Welcome to the second physics assignment methodology video. In this video, we will be going over electrostatics. Starting with question number 1. Question 1 states that Ulrich stands next to the Van de Graaff generator and generates shock as he holds his knuckles 21 centimeters from the machine. In order for a spark to jump, the electric field strength must be a certain voltage per meter strength. Now we need to find the voltage. Just by simply using the units given to us, we can find out that the voltage per meter constant or value times the meter value will result in simply the voltage value. So in this scenario, you would take the given voltage per meter value of the electric field strength and divide that by the distance or meter value, and you would get the voltage. Simple enough. And now the second question states that a lightning bolt from a cloud hits a tree after traveling 220 meters. The electric field strength is 1.68 times 10 to the power of 6 volts per meter, and you want to find the voltage or the potential difference. And in this scenario, you would do the same thing, evaluate the units, take the electric field strength, multiply it times the distance, and that would result in the direct voltage that you need. Make sure that you're putting this all in the correct units. You will end up getting a value of 10 to the power of 8 or 10 to the power of 5, depending on which question. And now question 3 asks, is it a good idea to stand under a tall tree? I will draw a small diagram of how this would be. We are going to imagine that there are clouds up in the sky, a set X distance from your head when you stand. Now there is a tree next to you, and if you were to stand under the tree, the distance is much shorter. Just evaluate how the distance change would result in a greater or lower charge being produced. It is pretty obvious just using logic of whether or not you should stand under a tall object, or just referencing what objects are more likely to get struck by lightning. And this question is simple as well. The fourth question states that the human body nerve cells work by pumping sodium ions out of the nerve cell in order to maintain a potential difference. There is a certain charge, it is pumped with a certain force, and the voltage is a certain value. You are asked to find the distance. In this scenario, what you would recognize is that by taking the electrical force value and dividing the charge value, you would get the electric field strength. So I will write that down. The force value divided by the charge value, I know you could write force as F, but I'm writing it with its unit as newtons, is equal to the electric field strength value. And now substituting this into the equation, that voltage is equal to the electric field strength times distance would give us the equation rewritten as the electric field strength all the way from here divided by our voltage value is going to give our distance value. Keep in mind that you will take the absolute value of your answer since you can't input any negative answers. And now moving on to question 5. Question 5 states that there is a auto body painter who applies paint. It is giving us paint particles experiencing an equal force and having a separation of a slight gap in centimeters. I'm going to highlight centimeters because you will need to convert this to meters, meaning multiplying it times 10 to the power of negative 2. Now, it faces a certain force, and you are given a certain distance. If you know the field force and you know the distance, you can plug in that the field force is equal to Coulomb's constant times the charges of the particles, and Q1, the charge of both particles, is equal. And so you would just say Q squared divided by R squared. The R squared value is the centimeter value, and you are solving for Q. This is pretty simple. Just rewriting this would result in the field force strength divided by Coulomb's constant times R squared is equal to Q squared. Square root both sides and you will get your answer as Q. Question number 6. Question number 6 states that while getting out of a car, Victor builds up charge on his body. You are given the amount of electrical potential difference and the field force, or the electric field strength. And I just want to state that if you are finding the distance between his hand and the car, all you have to do is evaluate whatever units that you have and just try to find the meter value as simple as possible. You are given the voltage and you are given the field strength, which is volts per meter. By taking voltage and dividing it by the electric field strength, you're in turn multiplying by the reciprocal, thus getting the distance. Simply divide the electrical potential difference value by the electric field strength to get the distance. Question 8. After unpacking a shipment, Mrs. Payne dumps the box of styrofoams into a recycling bin, and the chips rub at a distance of a certain meter apart. The force of repelling is a certain Newton amount. You are told to determine the charge of each of these chips. In order to find the charge of each of these chips, you would essentially do the same thing where you're given the field force, and you would just solve using Coulomb's constant times the charge of the chips. We're assuming they have equal charge, and you would take the distance value and square that. Same thing as we did for question 5. You would input the same equation and solve for your values. Question 9. This is another nerve cell and sodium ion question with the Newton value, force value, the charge value, and you are to determine the electric field strength. If you are given the force value and the charge value, you know that newtons per coulomb is equal to the electric field strength. So take into consideration the force value and the charge value, divide them, and you will get the electric field strength. Question number 10. A particle of ink in an inkjet printer carrying a charge of a certain value is deflected onto the paper with a certain force, and you are asked to find the electric field strength. This is pretty much the exact same as the previous question, as you are given the force, you are given the charge, and newtons per coulomb is the unit for electric field strength, and it is pretty much the same question as question number 9. Question number 11. Two Van de Graaff generators whose centers are separated from one another by half a meter each become charged after they are switched on. One Van de Graaff generator holds a certain charge, while the other holds a certain charge. Determine the magnitude of the electric field halfway between them. This question is a bit more complicated, and it requires a free body diagram. We will assume that these two rectangles are the Van de Graaff generators. The distance between these generators is 1/2 meter. We are told to find the field force halfway between these two generators, meaning that the distance from one generator to the halfway point is 1/4 of a meter, and the same applies to the other generator. Now, the information that we do know is the charge of each generator. I will label this as charge 1 and charge 2. I will assume that the generator with the negative charge is C2. Now, in order to find the electric field force contributing to a object halfway between these two generators, you need to visualize the electric fields. Suppose that this circle is the electric field of the first generator, and this circle is the electric field of the second generator. These are two independent electric fields, and they will each contribute to a vector force. Now, in order to find the electric field strength of each independent generator to the object, what you will be doing is finding, you will be finding the electric field strength through using the simple equation of the electric field strength is equal to Q source, which is C1 in this scenario, divided by R squared, which is just half the distance. Keep that in mind, this is half the distance. I should probably put that in parentheses and erase that portion. But R is half the distance. And you would multiply that times Coulomb's constant. This would be the electric field strength of this electric field. In order to find the electric field strength of the second field, all you would do is essentially change C1 to C2, and you would get the electric field strength of the second generator. Once you find the electric field strengths, you will realize that there are two counteracting vector forces being placed on these electric field strengths, one being positive and one being negative. But what you need to take into consideration is the definition of an electric field. Electric field forces always move in the direction of a positively charged ion. Now, in this scenario, you are given a negatively charged ion. You will need to consider whether these vector forces are now in fact moving in opposite directions or in the same direction. If they are moving in the same direction, vectors will be summed. If they are moving in opposite directions, the vectors will be taken as a difference. Whatever value you attain after either adding or subtracting these vector forces will be your final answer. Question 12. It refers to the previous question and asks for the direction of an electric field. Once again, the direction of the electric field is in the positively charged. But in this scenario, what you need to take into consideration is which direction will an object move. Will an object move in the same, will a positive object move in the same direction as a positively charged ion, or in the opposite direction of a positively charged ion? To ask yourself this, take into consideration two magnets. If these two magnets are faced with two positive charges, would they attract or repel? And now if these two magnets were facing in opposite directions, with the negative side facing the positive side, would they attract or repel? take into consideration this and visualize it in this scenario to determine whether a positively charged ion will be attracted to the negative or attracted to the positive. Question 13. In the 18th century, it was a common practice to ring the church bell, and however, okay, this is just a bunch of history material that is unnecessary to the question, but we are given that a bolt of lightning discharges at a certain charge, and the electric potential difference from the cloud is a certain voltage value. Determine how much energy is lost. Keep in mind that potential energy is equal to nothing but the voltage times the charge. This is because a volt is defined as a joule per coulomb. I'm spelling coulomb wrong, but I'll just put C for this scenario. And in order to attain the joule value, you would take the voltage times the charge. The very final question, question 14. Millikan oil drop experiment of 1909 allowed a scientist to determine the charge of an electron, and we are given a similar question to earlier where you have a oil drop which is suspended between two charged plates. And this oil drop has a certain mass. I will put M as the mass. And you are given the electric field force. One thing that I just want to quickly check over. I believe there was a very similar question earlier in this format. And there in fact was. Question 7, we had entirely skipped. And this was for the reason that both of these questions are very similar in concept. When it comes to question 7, it is stated that you are given a certain mass, you are given the electric field, and you are asked for the charge. In order for the mass and the electric field to be balanced, what you need to realize is that the potential energies are set equal. And in order to find the potential energy through gravity, you use mgh. The potential energy through, the potential energy through gravity is mgh, while the potential energy through electrostatics is the negative of the charge times the electric field strength times the distance. What you need to realize in this equation is that the height and the difference are the exact same, so they can cancel out. So mg would equal the negative of the charge times the electric field force. You know the m value, g is constant as 10. You know the electric field value from this question, which is directly stated as 5.847 times 10 to the power 5 newtons per coulomb. And you would take the mg value and divide by the E value to get the Q value. Make sure to take the absolute value of the Q value since the question doesn't allow you to submit a negative value for Q. And now going back to question 14, we have the same issue and we have the same values. You may be thinking, how do we find the number of electrons? If we were to find the charge value in the same method that we used in number 7, you would get the charge of this suspended object. The charge of the suspended object is going to be the charge of a singular electron times the number of electrons. And in order to find the number of electrons, which is our goal, we would take the charge divided by the charge of an electron. You may be asking, what is the charge of an electron? It was stated at the very beginning as the charge of an electron is 1.6 times 10 to the power of negative 19 coulombs. By taking the charge found through a modification of the potential energies equation and dividing it by the charge of a singular electron, you will get the number of electrons. And as specified in this question, please make sure to round to the nearest whole number. And I hope that this methodology video has helped.